All righty. We are going to keep on going today with section 4.2. So we were talking about discrete probability distributions. And under the umbrella of discrete probability distributions, there are specific structures, specific formats of these experiments that we can run that show up kind of often and produce very convenient results. So we're only going to practice with one of those. And this one that we're going to talk about today is called the binomial probability distribution. It turns out you can create this type of distribution more often than you think, but it does have specific rules that need to be followed, 1 through 4. So the experiment is performed a fixed number of times. Each repetition is called a trial. So from the beginning, you know, hey, I'm going to pick 10 people. Hey, I'm going to do this 5 times. Hey, I'm going to do this 70 times, whatever. The trials are independent. So each time you do whatever you're doing, throwing, rolling, picking, choosing, the probability can't change. What happens before doesn't affect what's going to happen next or now. For each trial, there are 2 outcomes, 2 mutually exclusive or disjoint outcomes, success or failure. That's all we really care about. Their success or failure. So this and not this. And then the probability of success is the same. The same. 2 and 4 are very, very similar. So you might combine them. Different groups might only have 3 bullet points, but trials are independent and the probability of success are the same. But that probability being the same is important. So just some notation to get used to. There are n independent trials. So the sample size is n. We're going to let P denote the probability of success, which means Q is the probability of failure. And if that's the case, we know that P plus Q must add to 1, right? That's the only way that that can be true. P plus Q must add to 1. And then, last but not least, let blank be a binomial random variable. Let big X be a binomial random variable. So X is the number of successes. That's going to be what we hold on to here. X is the number of successes. So X is between 0 and n. So let's look at them. Some of the examples we're going to do is just kind of yes or no, true or false. Is this binomial or is this not? And let's talk about why. Player rolls a pair of fair die 10 times. The number X of sevens is recorded. Okay, so we look through our bullet points, or 1 through 4. The experiment is performed a fixed number of times. Yeah, we know how many times it's going to go. It's 10 times. Sweet, no problem. N equals 10. The next bit, the trials are independent. I'm like, okay, well, yeah, it's not like when I roll the die one time, the next time I roll the die, it has memory. It doesn't know what's going to happen before. So independent. The third one's a little bit tricky here, so I want to skip it. The fourth one is the probability of success the same. Will it change? If I don't get a 7 on the first time, will it increase my odds of getting 7 on the next time? And as much as some of us might want to say yes, turns out no. Your odds stay the same every single time. So P is equal to 1/6 every time. Check. Now, is there success or failure? Is there success or failure? So we know that success, the P, lowercase p, is probability of a 7. But it seems like there's more chances, right? There's 6s and 5s and 4s. So man, there's not 2 mutually exclusive outcomes. But if we kind of alter our thinking, we can say Q is the probability of not 7. So we're good there. So yes, this one is most certainly binomial. Yes, binomial. The next one, the 11 largest airlines had an on-time percentage of 84.7. Okay. In order to assess reasons for delays, they randomly select flights until 10 that were not on time. Let the number of flights X that need to be selected, sorry, the number of flights X that needs to be selected is recorded. Okay. So reading through this, what do we think? Right, maybe press pause for a second and see if you can get there yourself. But after pressing pause, hopefully you can see it is not binomial. And it's because we're choosing until we get to 10. So we don't know. Randomly selects until she finds 10. So I don't know what n is. N is not, how do we say, fixed. N is not fixed. Okay. So we know how to tell if it's binomial or not. So why do we care? So we're going to skip this little space real quick. We're going to come back to it and hopefully to see some of the importance of binomial. So let's look at this little thing. According to the Air Travel Consumer Report, the on-time percentage is 79%. Suppose that 4 flights are randomly selected. Okay, so I know N is 4. X is the number of on-flight times. So what we're going to do is we want to create X, probability of X, with 0, 1, 2, 3, and 4. I'm choosing 4 flights. I know N is 4, P is 0.79, and hopefully you can figure out that Q is 0.21. Awesome. So let's find the probability X equals 0. You have 0 on-time flights. So probability X equals 0 is 0.21 times 0.21 times 0.21, 0.21. No problem. And that equals, throw that in your calculator, 0.21 to the 4th. Let's say 0.002. Sweet. Okay. Now let's start to look at probability X equals 1. And I really don't want us to write this down right now because it's going to clutter the space. I just want you to watch how difficult this might be. So I have 1 flight on time. Probability X equals 1. That's going to give us, 0.79, 0.21, 0.21, 0.21, no problem. But here's the issue. And remember, we're not writing this down. This is wrong. This is wrong. Hopefully we can see why. But the main issue is that we don't know if it's the first flight that's on time. So we play this game. Okay, well, what about 0.21 and it's the second flight's on time? Okay, well, now we need to consider the third flight on time and now the 4th flight on time. So there's going to be 4 more lines like this. And again, you're not writing this down. And then for probability X equals 2, there's going to be 6 lines because it gets even trickier. Again, don't copy this down. I just want you to watch real fast. 0.79, 0.79, 0.21, 0.21. Then we have to consider when it's P times Q times P times Q. And then P times Q times Q times P, and all these situations. So it gets really, really ugly. But hopefully, you can maybe see a pattern in X equals 1, right? That 0.79 is going to keep moving down the list. And when we have x equals 2, there's a pattern as well. Not as easy to see, but there is a pattern. Whenever there's a pattern, there's a nice, neat formula. So our formula for this situation, for this binomial experiment, will look like this. The probability that big X equals some number of successes, 0, 1, 2, 3, is going to be the combination N, C, the number, P to that number, that's the number of successes, and then Q to the N minus the number. Now that might feel terrible, right? And it looks terrible. How am I going to type this in? It doesn't feel right. But whenever there's a nice, neat formula, our calculator has a nice, neat function for it. So now we look at the calculator instructions. So we're going to have here the probability that X equals some number is going to be, and I'll show us where this is in a second, binom, PDF. And if you were to type it out each time, it's going to look like the number of trials, N, the P, probability of success, comma, the number of successes that you care about. So, again, hopefully we didn't write that down. In this first case, we should have got binom, PDF, 4.79 and 0. Let's see if we get the same answer. So go ahead and open up your calculators. And let me switch the camera here. All right, so where we're going to go is we're going to get that distribution right there. It's behind the vars button. So we're going to go second. Well, let me quit first. Get to the home page. Second vars. And when you scroll all the way down, there's a binom PDF. Keep in mind that CDF is below it. We're going to use both. But for right now, it's just PDF. You type it in. What are the trials? 4. What is the P? 0.79. And the X value for now is 0. And there's our answer. The same exact answer as we got before, 0.002. So I hope that that's making some sense. 0.002. So now what I'd like you to do is go ahead and try it for the next 3. Or 4 examples. Find the probability X equals 1, probability X equals 2, and then so on and so forth. Fill in these blanks. I'm going to press pause here, and hopefully you do too, so you can find the answers yourself. Please feel free to try it now. So there's that there. Hopefully that didn't feel too terrible. Oop. Yeah. So now we can start to ask you questions like, hey, what's the probability we get 2 or more, or less than 3, or something like that? And we will ask those questions. And we can always create a table and just add things together, and it wouldn't be too bad. But what if N is 30 or N is 50? N is 100 sometimes. This would be very frustrating to create that big of a table. So what else can we do? Well, our calculator has another function that I pointed out earlier, binom CDF. x equals, and what this tells us, it's a little bit particular. It only tells us the probability x is less than or equal to some number. Only less than or equal to. So if it's greater than or equal to, just less than, we have to make adjustments. Binom, CDF, N, P, and then the number. And this is where things get a little bit challenging. It is kind of translating the English to the math. And it's going to take a second. We're going to make some mistakes, but we will get used to it. So perhaps to help out here, if it says at least, no less than, greater than or equal to, it's right here. That's the symbol you want to do. More than, greater than, right there. Fewer than or less than, looks like this. No more than, at most, less than or equal to, it's right there. And then exactly, equals, or is that. So if you want equals, you do PDF. We don't use PDF nearly as often as we do CDF. So just something to keep in mind. But let's look at some possible future quiz/test style questions. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. Fine. Let's randomly sample 20 car-owning households. What's the probability that exactly 5 have 3 or more cars? So not too bad. N is 20. P is 0.35. And I know it's equal to. Probability X equals 5. So it's binom PDF. So you look this up, binom PDF, and just give it what it asks for. It asks for the trials, which is 20, the P, 0.35, the X value is 5. So hopefully you're finding this on your calculator and getting this answer. You know, of course, you don't need to write all this out every time because most of your answers or your problems don't require you to show work, but I just want you to see how I'm doing it. Okay, no problem. Now this next one, now we may have a problem. In a random sample of 20 car-owning households, what's the probability that less than 4 have 3 or more cars? So I want to know probability X is less than 4. But again, our calculator cannot tell us this. Look at what our calculator can do. Less than or equal to only. But since we're in discrete, what's the same thing as less than 4? It turns out it is probability X is less than or equal to 3. Because if you were to count it out, less than 4, 0, 1, 2, 3. Less than or equal to 3, again, 0, 1, 2, 3. It's the same thing. But now, thinking about it this way, my calculator can help me. So we tried again, binom CDF, 20.35, 3. You roll that in the calculator. And we get 0.04. Oops. 0.04. So not too bad. Hopefully that seems like it feels okay. But now what about this next one? Probability at least 4. So I definitely would like you to press pause and try this on our own and see if we can get this before I get there. Probability X is greater than or equal to 4. So please press pause and go ahead and try that. Hopefully we've unpaused and we've all come to the conclusion that this is the same thing using our complement rule as 1 minus the probability X is less than or equal to 3. Because this 4 was 4 through 20. 1 is all the situations, that's 0 through 20, and less than or equal to 3 is 0 through 3. So by taking 0 through 20, subtracting 0 through 3, I achieve the same thing, 4 through 20. there's a whole bunch of different ways you can draw a number line to achieve this or logically think through this. So whichever way you find works for you best, please do it. Because it changes. If that's greater than 4, my situation's different. But I look at the answer above, and I already found the probability x is less than or equal to 3. So I know it's 1 minus 0.04, which is 0.96. Nailed it. And I'll let you know, if we didn't use this function, if we didn't take advantage of this, trying to situationally break this down, like with successes and failures with P's and Q's, and order it and keep track of it, would take 2 to 3 pages or something like that, and a whole bunch of time that we would waste. So this is so much nicer. So it's nice to recognize when patterns like this show up, this binomial situation. And this does happen in some algebra situations and other, situations in chemistry and physics. And there are other organized distributions like this, the Poisson distribution. I can't think of any other ones off the top of my head, but eventually we'll get the normal distribution. So yeah, that is binomial distribution, binomial probability. A couple other things before we finish up here with binomial distributions. The mean and standard deviation, very easy to find. Right? Before we had to, plug it in our lists, x times probability of x. And again, if n was like 30 or 40, that's a big list to enter. But if I know it's binomial, pretty convenient. Mu of x is n times p. Just multiply. And sigma of x would be square root of npq. Pretty nice formulas to fall out right here. So just using those formulas, something that could totally exist on a note card, I would like you to go ahead and try to find mu and sigma for this example. Again, please press pause on your way to get there. So for those of you who have unpaused, let's look at the answers. Mu of x, NP, 400 times 0.35. Nice, neat 140. That is the mean. Sigma of x, square root NPQ, square root 400, 0.35, 0.35, 0.65. Throw that in your calculator, we end up with 9.54. What you do with these values, that's up to you and the situation and why you're calculating it, what business decisions you might be making, or pricing options you might be creating. But the point is, we know how to find the values now. Sweet. So in the past chapters, we've put some importance on a distribution being bell-shaped. And it turns out there's a way to double check if my binomial distribution matches a bell-shaped distribution. And what we're going to do here, consider the graph of the binomial distribution. For a fixed p, as n increases, the probability distribution variable of the random variable x becomes bell-shaped. Bell-shaped. So you can see it has like a slight skew here. This one has a small skew, not very much, and this one's almost perfect. Okay. And to check if something's bell-shaped, as a rule of thumb, the probability distribution will be approximately bell-shaped if NPQ, is going to be greater than or equal to 10. So if I ask you, hey, is this normal or not? Or I'm sorry, is this bell-shaped or not? That's all we need to check. Is NPQ greater than or equal to 10? We can use the empirical rule to identify unusual observations in a binomial experiment. It's not something we're going to do that often, but just to kind of know, any observation that lies more than 2 standard deviations away from the mean may be considered unusual because the observation occurs less than 5% of the time. So let's check this out. Hey, we got that same situation from earlier. We sampled 400 cars, and we know that mu sub x is 135, sigma sub x is 9.5. And we got to check, hey, is 162 an unusual amount of households to have so many cars? So you can draw a little bell curve real quick. 135 in the center. I'm just going to put 2 notches because that's all we really care about at this point. I'm going to add 9.5. We get 144.5. I do it again. I get 154. I can go down if I want as well. Just real quick, might as well. And I get 125.5 on this side. And then 116. And basically, since 162 is greater than 154, it is unusual. You can also just find the probability for these questions. If I ask you, is something unusual? Find the probability. If the probability is less than 5%, we are thinking it's unusual. Probability, x equals 162. This is binom PDF. Binom PDF. We throw this in. I'm running it alongside you. 400.35, 162, and we get 0.003. 400, 0.35, 162, 0.003. So definitely unusual. That's very, very small. So I hope this lecture made sense. This is one of our more difficult topics, so definitely give it a little bit more time than maybe some of our previous sections. But if there's any questions, definitely email me. And other than that, good luck with this section.